I will be presenting agent design contracts or how to sell it in action. And this is a joint work with Matteo Castiglioni and Andrea Celli. So, okay, I guess we all know here what's a principal agent problem, but very briefly, we have a principal which designs a contract and an agent which performs an hidden action. And for example, here we can have like we are a developer who wants to build a skyscraper, and we need to hire like a construction worker company. And but this construction worker company, we cannot directly observe the level of effort put into building the walls of the skyscraper or whatever. And so the agent, we say that performs the hidden action. So a little bit more formally, like a classical contract design problem, we have that the uninformed party, the principal, is the one designing the contract. And uninformed here refers to the fact that the principal is not informed about the action that will be taken. While the agent is the informed party and is informed about the action that will take in the game, and is the one also performing the action. And each action leads to a stochastic outcome, which is then mapped into payments by the contract. The question that we want to ask in this talk is, what if the contract is designed by the party which also performs the hidden action? And sadly, like very recently, I discovered that like a standard textbook in contract theory says that the case in which the informed party also designed the contracts has no real world applications. So, okay. But this is a slightly old textbook, and I think that recently the development of economic theory into some aspect of web interactions, online interactions, made this problem a little bit more reasonable. Okay, let me, so I will try to convince you about this. So we kind of do a little trick to this interaction, and we have that the informed party also designed the contracts. The same party that designed the contracts also performed the hidden actions, which still leads to a stochastic outcome, which is then mapped to a payment contingent to the outcome reached. A small example now, let's say that we are a client and we want to train a machine learning model. But we don't know how to do it, so we just provide the data to a cloud-based service provider, which takes care of the training process. But actually, this training process is hidden from us. So if we go to a pricing homepage of one of these AutoML kind of frameworks, there are a lot of them, but they all look kind of similar to this one. So here they ask us to pay for $0.2 for 1,000 predictions. But okay, it's reasonable that we trust them. But what if they are in fact needing more compute, and for some of our predictions they do not have the computational power to do it in that moment, and they will output random predictions. So it's fine, but the current framework for this is all completely based on trust. And here we kind of like incentives more than trust, right? In general. And okay, let me unpack a little bit more formally the model. A user is drawn from a type distribution, and the service provider commits to a contract. The contract is made of actions, and each contract in the menu is comprised by an action and a payment scheme. So A is the action, the promised action of the contract, and P is a vector that specifies a number for each of the possible outcomes. And the client then selects his favorite contract here, and the service provider now performs an action, which is hidden, so it can be different from the one promised. This leads to an outcome through a distribution function f, and each outcome then maps, also jointly with the selected contract, maps to a payment to the platform from which we have to take out the cost of performing that action, and a reward for the client, which depends on the type and how. So this is the model of agent design complex. We said that we like incentives more than trust, and so an incentive compatibility menu here is defined as each promised action in the menu is a best response to the expected payment minus the cost. So for incentive compatible menus, it's fairly reasonable to assume that the promised action will be performed. Okay, so now we will delve into a little bit the computational aspect of this problem. And the first is a bad news. So the problem is not approximate, the optimal menu. But the optimal menu could be large. So if we have a large set of actions and a large set of types, the optimal menu could be arguably because of both of these are large, but in practice it's reasonable to ask what happens if we would like only to present a menu which is comprised also only by a small number of contracts, because we don't want to overwhelm the client with a choice over, let's say, thousands of different contracts. And so let's first solve the problem with a fixed number of contracts in the menu. And so this is the program that we have to solve for a fixed menu size k. We want to maximize over the menus, so actions and payment schemes, payment vector P. And this is the expected service provider utility. And the constraints are the incentive compatibility constraints. Okay. Let's rewrite this in a slightly different way. That will be very helpful computationally and also to understand better why in this problem we are actually selling actions. And okay, the incentive compatibility constraints are of this form. Note that in the program we only care about the expected payment. So the vector of payment P only appears when multiplied by the distribution function F. And so we only care about expected payments. And so we define the expected payment Q for each action. And the set Q of A defines the set of expected payments for each action that makes that action incentive compatible. So we can rewrite the problem as this that I refer to as a pricing problem. I will tell you in a minute why. And the set QA, so we only care about the expected payment, I was saying, and the set QA is of a special form, which I refer to it as a price floors, because it only defines a lower bound on the price to make that action incentive compatible. Quite easy to see. So let me tell you why I call to this reformulation as a pricing problem with price floors and the unit demand, because we can interpret this program as we need to select some item A, some bundle of items, and price them. So we have buyers of types theta, distribution over types. We have an expected payment for each one of the actions, which are items, and these constraints on the prices are lower bounds on the price, so price floors. And the buyer has unit demand and some utility, which depends only on the action and its type. And it will decide an item to buy. And after he decided which item to buy, the seller will actually build the product and pay the cost of production. Crucially, this is very important computationally because now this problem has only a number of variables which is linear in the number of items that they want to sell. While the original problem also depended linearly on the number of types. And the algorithmic idea to solve this is, okay, let's first observe that if we fix the actions and the choice function that maps types to items, then this is just an LP. But okay, in mind we have to keep that k is constant because we want menu small size. But the number of choice function that maps types to the item both, they are too many to iterate over. And but if we look closely, we can see that for each choice of the choice function that maps types to items, these are all polytopes sharing the same hyperplanes. So we can, for each tuple fixed, we can at the same time enumerate over all the vertices of the polytopes, but at the same time without having to enumerate over the choice functions. And this has a computational time which is exponential only in the number of items that we want to set. Okay. And so if polynomial, if this is constant. This is in crucial difference with the classic contracts design, in which the optimal single contracts in Bayesian setting is NPR to compute. While here, if we ask for small menu complexity, we have polynomial time algorithms. And as a simple corollary, also, if we have a small number of actions or types, we know that the menu has a small size, the optimal menu is small size, and so we have polynomial time algorithms for solving this problem. Okay, also the characterization, we have a characterization of the utility that can be extracted by this by menu of small size, which is k, the size of the menu, over the minimum between the number of actions and the number of types. So it grows, you can argue that this gives enough, and this bounces type. So it always gives this, and there are instances which this is the best you can do. We have some additional result to this problem. For example, we have we thought about the problem of continuous actions, in which the action is continuous, and this makes sense for the problem that we started from, so training machine learning models in cloud-based platforms, because this could be like the time spent training the model, for example. And we have that if some regularity conditions are met, for each constant approximation that we want, there's a polynomial time algorithm, which is if the approximation is epsilon EC for the service provider, and gives a utility which is epsilon far from the optimal one. Note that the burden of rationality here falls on the service provider and not on the user, because we don't know how the user will perform. So algorithmically we converted like epsilon individually rational and incentive compatible constraints of the user with a small amount of linear contracts. We converted into epsilon EC for the service provider, which we think that as a model makes more sense. And also we looked at the menu of randomized contracts, in which the menu is not comprised by actions and payment schemes, but by a randomization over actions, and for each randomization over action, also a payment for each action. And this is both computationally very efficient and also utility-wise very efficient, because we could show that randomized contracts, in this randomized menu of randomized contracts gives utility which is number of types multiply better than the deterministic ones, but also there always exists a polynomial time algorithm to compute them. Okay, that was it, and thank you for listening.